Hi, I'm Craig Gentry, CTO of TripleBlind, and I'll be talking about FHE, partly from, my self-indulgent perspective, the past 15 years since my thesis, basically. So that's the past. The present, I'll give, someone working in industry, I'll give some thoughts on the maturity of FHE as a product and what we can do there. In the future, I'll give some, I guess, some predictions, but mainly I'll focus on one result that I really like from the past 2 years that I would like to see improved so that it actually becomes usable in the future. All right, so with that, this works. All right, so the past. So in the deep past, basically right after the invention of public key encryption by RSA and Diffie-Hellman, two of those guys, Rivest and Adelman, and also Dertouzos, proposed the idea of fully homomorphic encryption. They called it a privacy homomorphism. And basically, they had this idea of cloud computing, where basically, and they didn't call it that because we didn't have that terminology, but they had this idea that you could just outsource a computation to someone with more resources, the cloud, and while preserving your privacy. So of course, you would want to encrypt it first and have the cloud do the computation on your data while it's encrypted. And the question, basically was, can you delegate the processing of your data like that without giving away access to it? So just to make sure that we understand the problem, I'm sure all of you do, but for completeness. So here's the setting diagrammatically. So we have Alice here. She has data, and she wants to use cloud computing to, basically handle her data. So first of all, she's going to upload all of her data encrypted, and then later she's going to come back and she's going to want to download some of that data or some function of that data. So what she can do is she uses this special scheme. She encrypts her data X, and later sends a function F, which could be encrypted also. And then with the special privacy homomorphism, the cloud can run an algorithm called evaluate that takes the function and the encrypted data as input and outputs an encryption of the function applied to that data, the response that Alice wants. And then the cloud sends that back to Alice. And the cloud never sees anything. Even if the cloud is breached, the attacker won't learn anything because it's encrypted. So the encrypted response goes back to Alice, and she can decrypt and recover the response that she wants. So that's the basic problem. Rivest, Adelman, and Dertouzos had this idea basically, well, like 45 years ago now. But it took a while to realize it. Meanwhile, there was something being invented called lattice-based cryptography. Back in the 1980s, it was known as knapsack-based crypto systems. But these guys here, Lenstra and Lovatz, invented the LLL algorithm, which is a lattice reduction algorithm, which broke basically all of these lattice-based crypto systems. And all, people continued inventing lattice-based crypto systems well into the 90s and beyond, and it kept breaking. There are researchers that made sort of a whole career out of breaking knapsack-based crypto systems using the LLL algorithm in various clever ways. So I kind of became a cryptographer sort of on the tail end of that phenomenon. So I started off using, being kind of destructive against lattice-based cryptography. So my first few papers were all breaking various versions of Gentry signature schemes. The Gentry encryption scheme, it turns out, is doing pretty well. But the early Gentry signature schemes, not so much. So had a great time breaking them. using the LL algorithm and other fun number theoretic techniques. And so that's how I got started. And from my perspective, of course, this being my work, lattice-based cryptography didn't seem very promising at that point. So I moved to pairing-based crypto. So pairing, back in 2001, we had the first identity-based encryption scheme, Bonnet-Franklin. And there's all sorts of other stuff that could be built from bilinear maps, like hierarchical identity-based encryption, various, attribute-based encryption, all sorts of things. It was a new Swiss Army knife back then. But there was kind of an interesting premonition. So Bonnet and Silverberg considered, can we construct multilinear maps? And so if you had a multilinear map with arbitrary degree, then basically you would have fully homomorphic encryption. So out of bilinear maps, we get encryption schemes that can kind of handle quadratic formulas in the underlying plain text. If we had multilinear maps allowing arbitrary degree, then that would be fully homomorphic encryption. That would allow you to do arbitrary encrypted computation. But in their paper, they had this insight that even to do a trilinear map, it would have to be a very strange sort of thing, and it wouldn't really fit in the same sort of rubric as bilinear maps. They said, we give evidence that such maps have to either come from outside the realm of algebraic geometry or occur as unnatural computable maps arising from geometry. So that sounds a lot like lattice-based crypto. I mean, in retrospect, I'm not saying they anticipated that you could do multilinear maps from lattices, but that is what ended up happening. So meanwhile, lattice-based cryptography was sort of maturing. So Gentry, I mentioned, and the Gentry signature schemes. The Gentry encryption scheme has held up pretty well. And it really, it was, a forerunner of the ring LWE problem and so forth, ideal lattices in crypto. So they were really the ones that started that field. Also, ITI and Dwork proved worst case average case reductions for lattice problems and based a crypto system on that. And most notably, Oded Regev invented the LWE problem, the learning with error problem, that we all know and love. He was also an author on the ring learning with errors problem. So really, lattice-based cryptography was maturing during this phase. And that's about the time in 2005 that I started my PhD. I did everything kind of backwards, by the way. I went to law school for a time, and then I went from there to being a crypto researcher, and from there to getting my PhD. So it was all kind of backwards. So in 2005, I started my PhD, and my advisor, Dan Bonnet, said, at the PhD orientation, first day, says that, anyone who solves this problem is basically an instant PhD. So I'd like to say that I was motivated instantly and worked on that doggedly for the rest of my PhD program, but that's not quite what happened. But it did stick in the back of my brain. So for a few years, I was developing sort of a Plan B thesis, sort of around all this pairing-based stuff that I was doing. I mean, there were some, IB schemes. We also had IB schemes also based on quadratic residuosity, and in 2008, based on lattices with Vinod and Chris. So I had this, kind of nice Plan B thesis going, but, it wasn't fully satisfying, I guess. So I got to thinking again about this old problem, and started off with a simple observation that I mean, certainly it was obvious that lattice-based crypto systems are additively homomorphic, right? You can just add the lattice vectors, and you add the underlying plain text. And then, as I thought about it more, I mean, I had worked on breaking entry in the past, so I was pretty familiar with ideal lattices and sort of the multiplicative structure there. And so it was kind of clear that you could also multiply lattice vectors, and basically have the effect of taking the product of the messages. So could you get FHE from lattices? There were kind of other people that already made kind of similar observations, like around cryptosystems over the integers, for example, that you can do this with integers. And so here are some of the folks here. But as you add and multiply, the noise grows, and so you kind of run out of steam, as you know, in these crypto systems. You lose the ability to do operations eventually. So luckily enough, one day just working in a cafe, I thought, well, what would be a cool function that an FHE scheme or that an HE scheme could compute? Sort of the coolest, it kind of answered itself. The coolest function would be if it could evaluate its own decryption function. I mean, I didn't exactly know what the consequence of that would be immediately, but that would be just the idea of self-reference is kind of cool. Like Gödel Prize is kind of one of my favorite books. I just all this mythological stuff. I guess I get into it. So it just seemed like it would be a super cool idea. And then, but it didn't really take long after that to say, hey, well, if it could do its own decryption circuit, well, that would mean that you would just get back an encryption of the same message. And so what would the properties of that ciphertext be? So yeah, so at that point I was pretty excited, and I told people that I just kind of glancing at it and saying, hey, lattice-based decryption is really simple, and hey, lattice-based encryption, homomorphic encryption can also do pretty complex circuits. So I thought, oh, well, it looks like it can decrypt its own circuit. I mean, I wasn't that cavalier about it, but I went and told people that I had this result, and I didn't check my result very thoroughly. So it turns out there was still some work to do. There's this squashing the decryption circuit step that I had to figure out, because turns out it didn't quite reach, but with additional computational assumptions, everything worked out fine. So so I sent this to Stock 2009, and they kind of looked at it, and they didn't really know what to make of it. So if you've ever had a paper shepherded, don't feel bad. This paper was shepherded. So so Shafi Goldwasser was my shepherd, and she was a very good one, and definitely made the paper a lot better. And we took out a lot of the sort of the theoretical worst case, average case results that ended up being in a different paper later, and which were causing which really needed to be removed. I mean, the paper was complex enough as it was. So so yeah, so and as part of the shepherding process, Shafi said, why don't you describe this at Dogstuhl? And so I just remember one time describing it to Yevgeny Dodis, and I said, well, yeah, it's pretty simple. I mean, you just have it in, have an encryption scheme that's capable of its evaluating its own decryption circuit. Lattice-based crypto has this property, with some modifications, and then you can just go on forever. It's like that. And so and he was like, but where's the beef? And then Shafi said, well, that's the thing with recursion. At the end of it, you don't understand what you've done. So, and I think that's pretty true. I don't think I feel like the whole scheme didn't really fit in my head for a while, not all at once. I mean, I could sort of look at different parts of it and see that it was correct, but actually fitting the entire scheme in my head didn't work for a while. So I was quite unsure that it all worked until my colleague at IBM, Shai Halevi, actually implemented it. And I wasn't entirely sure that it was all secure until Zvika and Vinod based it on LWE. Okay, so so what next? So after that, I mean, the reception was the reception was pretty good, but not uniformly good. So, for example, Butler Lamson said, "I don't think we'll see anyone using Gentry's solution in our lifetimes." And well, it turns out, well, he's right, because There's been a lot of other work on FHE that's improved it immensely. So shortly thereafter, we had the second generation of FHE schemes, which allowed all sorts of performance improvements. First of all, it had SIMD operations, so you could operate in parallel on 1,000 different slots inside a single ciphertext, whereas the first scheme just sort of assumed that there was one slot. And you have these, you can use automorphisms to rotate the slots so that slots from different plain text align in the right way. You can do multiplications and additions, so forth. And SIMD operations and rotations are basically complete for computation, so you could do anything. And you could do all this with only overhead that's polylog in the security parameter, which is just amazing. So this is what I was thinking at the time. I mean, I was sort of a theoretical sort of person, so I thought, well, I mean, the original scheme was efficient in the sense of polynomial time. This one is like, the overhead is only polylog security of parameter. That, I mean, what could be better than that? This must actually be practical. So I was like, all right, we're done. I mean, let's go implement this and change the world. So turned out not to be quite the case. But it did improve the speed immensely. So I mean, the overhead went down from incalculable, trillions. I think I mentioned the number trillion early on, but it could have been a quadrillion for all I know, because it couldn't be implemented. It was just too expensive. So, but the second generation of schemes really improved things a lot. And so you see this is a logarithmic scale, and you see Moore's law there just gradually decreasing. And algorithmically, we really reduced the overhead by a lot. So one qualification here. This is what in the early days we really avoided bootstrapping like the plague, because bootstrapping is really expensive. It still is. So these results here are without bootstrapping. We would just choose the parameters of the scheme big enough so that we could do the whole computation without bootstrapping. So that's what this is for. And then we had the third generation of schemes. So like FHEW and TFHE, which really achieved an amazing improvement in bootstrapping. So first of all, the noise growth in bootstrapping was much less. So basically, you see this lattice-based FHE as secure as PK. And that's because the noise in the FHE ciphertexts was basically staying as small as in the PK ciphertext using this new bootstrapping approach. Secondly, bootstrapping is programmable, so while you're refreshing a ciphertext, while you're bootstrapping it, you can also compute certain limited functions of the underlying plain text while you're doing that, basically for free. So that's nice. I mean, it could be a highly nonlinear function of the plain text that you're computing, still fine. And then stronger security, because again, the noise stays really small in this scheme, which means that everything is really tight in terms of security. Versus if you had a lot of looseness in how the noise could vary, then you would have to accept weaker security. So one drawback of the scheme is that, in the second generation, you could pack a lot of plain text into each ciphertext, but this is not natively supported in this scheme. But you have much smaller ciphertext here, so that's a trade-off. And then finally, you have the fourth generation of schemes. So the first and second generation are sort of like, plain text based is like mod P numbers. You do arithmetic. Third generation is mostly Boolean circuits. Fourth generation is like floating point numbers. So that's good for like neural networks. So this might be what you want to use for that sort of computation. The ciphertexts are kind of gigantic, but you can stick a lot of data in those plain text slots. And so actually, while bootstrapping individual ciphertext is really slow, it may actually be the fastest in an amortized sense when you amortize over all plain text slots. Okay, and then you have chimeric schemes, which can basically switch between different schemes. I mean, the whole idea of bootstrapping is basically that you can compute decryption within the homomorphic encryption scheme. So of course you can decrypt one ciphertext scheme into a different encryption scheme. So, and you can, depending on what kind of computation you want to do, you can switch from one scheme to another, depending on which one is the most appropriate. So my lessons learned, I guess, from the past is that I guess one is sort of be skeptical. I've always tried to be skeptical of an unproven consensus that something is impossible. So, I mean, one kind of consensus was that lattice-based cryptography cannot be secure, but the Gentry guys and ITITWork and Regev proved them wrong, and the results were quite surprising at the time. So one consensus was that FHE is impossible. So turned out not to be true. Today, you might say one consensus is that lattice-based cryptography is post-quantum secure. Maybe. I mean, I wouldn't oversell that. There was a recent proposed quantum attack by Yilei Chen that held up, he's a respected researcher. All the respected researchers were looking at his paper, and it took them 8 days to find the flaw. Not because the paper was poorly written; it was well written. It was a complicated argument, but it was a very subtle flaw. And this just shows, I think, that we don't really fully believe. We're not completely convinced that lattice-based cryptography is post-quantum secure, because the reaction to his result was, well, okay, yeah, maybe he's right. You could say another unproven consensus is that P doesn't equal NP. I mean, yeah, a lot of smart people have looked at that problem, but is that really good evidence for going down on one side or the other? Not necessarily so. So another lesson is that don't overfit on the poor performance of early schemes. I just find that people kind of get fixated on like an initial number or initial data point. So people still think of FHE sometimes as having an overhead of 1 trillion because that was an initial number that I threw out, which was kind of arbitrary, even though now it's in the thousands. And so I would apply the lesson here today to AI. So maybe we shouldn't overfit on the poor performance of GPT-4. I mean, it's probably going to get better. So if GPT-4 does some silly things now, it doesn't necessarily mean that it will in the future. And thirdly, never estimate the gap between theory and practice. I mean, we all know this to be true. I mean, just as a platitude, but it's one thing to sort of know it, and another thing to sort of experience it. So, so for example, like I thought quasi-linear time would be, I mean, come on, that's practical, right? But sometimes only truly linear is practical, and sometimes not even that. So there's a big gap. For the present, so I would say FHE is maturing. It's impressive how much progress has been made, how many researchers are researching the community, the efforts at standardization, the libraries, the toolkits. It's all it's just amazing to be a part of this and to see it progress so much. So I just took this because I couldn't make such an exhaustive list on my own. I just took this from the awesome HE. So here you have all the libraries here. I mean, some of them are more notable than others, but there are a lot of great implementations. They're great toolkits if you want to convert your code into a circuit suitable for FHE evaluation and so forth. There's all sorts of tooling for this. In terms of community and standards, of course, there's FHE.org. So thank you for inviting me to speak. There's homomorphic which is sort of a consortium of government and industry, which is focused on standardizing FHE. There are open source projects that are typically affiliated with one company or another, but are designed to solicit code from the outside. And there's this iDash competition. iDash hosts challenges, usually around biomedical applications, doing different models and that sort of stuff, and to benchmark homomorphic encryption and try to accelerate it. Their government projects, I mean, really early on, in the early days, there was a DARPA project called Proceed. So a lot of the first and second generation optimizations were made sort of in, for my part, in connection with that project at IBM. Currently is a DARPA project called Deprive, which is focused around hardware acceleration of FHE. So 70 million over 4 years. Intel is involved with that. And then there are standards bodies like NIST and in the EU, there's a Prometheus project, which is really focused around standardization of post-quantum crypto, but also, in connection and with an interest in fully homomorphic encryption. So, where is FHE getting traction? I mean, I think blockchain is really good for FHE because it's kind of it marries a lot of money to sort of an experimental spirit. So Zama, for example, has an FHE virtual machine for confidential smart contracts. So that's a really good application to kind of sink your teeth into, and that could be, if it works on blockchain, it could be extended in all sorts of directions. Another startup, I'm sure there are plenty, but another startup I noticed that does FHE, basically specifically private information retrieval to query the blockchain without enabling front running. So if you might query a certain block that you're interested in, but if the if the site that's responding to your query is doing a little double dealing on the side where they can say, hey, somebody's interested in this block, and they could sell that information to someone that might try to front run you, and so that you get a bad deal out of the transaction. So with FHE, that can be prevented. In terms of AI, progress is slower. I mean, for obvious performance reasons. So Zama has an interesting blog post where they estimate many orders of magnitude and cost reduction are needed for FHE evaluation of LLMs for it to be sort of reasonable from a cost perspective. For it to be like for it to cost less than 1 cent per token, basically. And they think most of that most of those orders of magnitude are going to come from hardware acceleration. So most of the algorithmic improvements are probably played out at this point, although some more will come, I guess. But a lot can come from hardware acceleration. But I also want to discuss, ways in which FHE is not really mature yet. So didn't know exactly how to do this without, kind of being negative. But if you look at, kind of just being in industry and looking at, what a real solution looks like, a real security or privacy solution looks like that people are actually buying. So one company is Wiz, which is like they shot up to unicorn level $1 billion valuation within a year of being founded, and I think just recently they raised more than $1 billion at I don't know how many, maybe $10 billion dollar valuation, just going exponential. And basically all they're doing is something simple, but it's something that customers are really looking for. So what do they do? So they're what is called a data security data security posture management solution. So, so they basically provide this one window into all of the security events that are going on for your huge company. And they sort of aggregate all the checks and alerts, and they just fit all of that into your workflow and even your development workflow, so that as you're developing, you're also simultaneously satisfying the compliance checks. So, so what do customers get out? So they get, visibility. Basically, they see everything that's happening. They get compliance. I mean, that's kind of what they care about. They want to check a box, and they get integration. They don't want to change the way that they're doing things. They just want it to fit into their workflow seamlessly and just work, right? And another one I look at that's really successful is a company called Datavant. They're basically in the medical area. They allow different hospitals and researchers to share record level medical data. So basically what they do is you have a bunch of patient records, and they have this tool which simultaneously just attaches a random identifier or token to the record, and then sort of de-identifies that record in the HIPAA sense. So HIPAA is a privacy regulation that requires you to sort of mask certain fields in certain ways. So they just, it's just tokenization and de-identification, very simple. And then, after that, basically a researcher can get, after using the token to sort of match records to ones that they might have, from their hospital, or to link records between different hospitals, they can just kind of follow the patient journey, across different hospitals and actually see the records, albeit de-identified, but they can actually see something. So again, they have this visibility that you can actually see some record level information. It's de-identified, but you can see some stuff, and you can see some patterns. You get compliance. I mean, it's sure, it's not as private as FHE or SMPC, but you do get this HIPAA compliance, and they attach what's called an expert opinion to it, which says that this solution is a good de-identification solution for HIPAA, provided that the users use the solution as they agree to in the user agreement from Datavant. So if you were to just take this de-identified data and cross-reference it with all sorts of other data, there are all sorts of re-identification attacks that possibly could happen. But you're supposed to follow this user agreement, and the expert opinion applies, or sort of assumes that users do follow that agreement, and in that case, you get compliance. And integration, I mean, this is just, researchers are sort of used to looking at record level data and just eyeballing it and just finding patterns on their own just by looking. And to some extent, the solution allows them to continue doing that. So if you compare this with cryptography products, they don't quite have these features in the way that users want them, so it makes it more challenging. So in terms of visibility, I mean, the privacy is not really observable. It's kind of in the background. The data itself is not visible in any sense, really. It's hidden. If you try to do exploratory data analysis or troubleshooting, you're trying to figure out whether a data set is interesting to you. It's hard to do that because you would have to do that in the encrypted space, presumably as some function that tells you whether you should be interested or not. But that's not really in the spirit of troubleshooting or EDA. Compliance, it sounds like, crypto solutions should be great for compliance, because they're sort of, we think of them as the most bulletproof security-wise. But from a business perspective, they actually introduce additional risks. So, I mean, if you're taking, this privacy solution and sort of deploying it right next to the company's most sensitive data, maybe inside the firewall, the lawyers have to get involved. There's something called third-party risk management. They have to look at that and say, well, is this solution doing what it says it does? Yeah, I mean, sure, if the solution does the right crypto, that would be fine. But then how do you verify that the solution does what it says it does? So there's this whole process of different types of risks that have to be involved, addressed. And then there's integration. So basically, cryptography products, maybe this is changing, but they can be quite disruptive to the workflow of how sensitive data is handled. Of course, the idea in the future is like with compilers like Concrete, you try to make this as transparent as possible, or you can just apply the compiler straightforwardly to computations you want to do, and you don't really have to worry about anything else. But it's a challenge to make it fit seamlessly into existing workflows. Okay, so and some more evidence that there's challenges ahead for cryptography solutions. So if you look at just like the market cap of very simple, I say simple solutions, I don't mean to be insulting, but I'm used to, I'm an advanced crypto sort of guy. But so things like tokenization, de-identification, federated learning, secure hardware, all to me seem kind of like simple solutions. But the market for those solutions is just much, much bigger than advanced crypto solutions. And I saw an exhaustive RAND report recently where, there's this whole issue of what do we do about the weights of frontier models? Like if the weights of frontier models get out to, our adversaries, maybe that would be catastrophic. So maybe we want to find a way to protect the weights of OpenAI's models. So how should they be secured? So there's just this exhaustive, maybe 100-page report by Rand on all the different methods that you could use to secure these weights. And there was quite an emphasis on confidential compute, HSMs, and kind of traditional supply chain security. Where did this data come from? Where did this model come from? But not, sort of the analogous software-based versions of those things, which would be, FHE, SMPC, virtual HSMs, basically, threshold signatures, for example. And cryptographic proofs for proving where models and data originated and how they were changed. So not much mention of that. Okay, so what are the sweet spots currently for FHE? So one thing I kind of see is, one thing is blockchain, just because again, sort of the money and the innovative spirit of blockchain is very good for advanced crypto. Another area that I think is interesting is private information retrieval, both because it is kind of, as far as advanced crypto goes, it is kind of a simple technology, and it also, in terms of performance, it's very good. So if you want to really minimize the overhead of FHE, private information retrieval is a good application to do that. So just to remind you what private information retrieval is, basically you have Alice here, and she has a key K, and she has some index I, and she wants to get the ith file or the ith bit from some database. Okay, so she just wants to pull down some bit of the database without telling the server which bit. Right. So it's a very basic problem, a simple version of fully homomorphic encryption. And there was, before lattice-based crypto, there was this claim, kind of this unproven claim, it turned out, by Sion and Carbonar, that really single server private information retrieval is never going to be practical. That it'll always be better just to go ahead and send the entire database. You get privacy that way, just go ahead and send it all, because the computation involved on the server side of a private information retrieval scheme is always going to be more expensive than if the server had just sent the whole thing. And this is back, I think, in 2007, before a lot of these lattice-based schemes. And so this is true kind of like of discrete log-based homomorphic encryption schemes, private information retrieval schemes, such as using Pallier, for example. But, it turns out that claim was wrong. So, it didn't apply to lattice-based private information retrieval schemes, which are many orders of magnitude faster. And they kept getting faster and faster. So I had one paper on this with Shai Levy, where basically we could get the server has, during private information retrieval, the server has to process its entire database to respond to the query. But we showed that it could do it in a way that the amount of time spent on processing its database to respond to the query is basically the same amount of time that the server would spend as if it had AES encrypted the entire database. So basically, the pure processing was as fast as AES encryption, which is pretty remarkable. And it kept getting faster and faster. So Samir Menon had a talk here at FHE org a year or two ago, where basically he used private information retrieval to set up a scheme where if you wanted a Wikipedia article, you could just type in the title of the Wikipedia article, and it would send sort of a private information retrieval query to the server, and you would get back the article that you want. So basically, it handled essentially all of Wikipedia. The images were stripped and some things like that, but basically all of Wikipedia you could do a query on, and it would just respond in basically a second. And it was, he had a pretty interesting talk here if you want to see it. So, kind of discussed why he thought PIR was sort of the killer app for FHE. There's nothing complicated, right? I mean, it's not a complicated data collaboration app. It's, there's no PKIs. It's a single party product. Get privacy right away. Low overhead for FHE. And in addition to Wikipedia, he had another application was, I guess I mentioned this before, that if you want to scan a blockchain, you kind of want to hide which blocks you're interested in. Otherwise, someone might front run you, and so you get a worse deal. You can do private malware scans, so you can scan for malware without revealing exactly what malware trace you're looking for. So these were kind of the applications he was looking at, and he kind of described some real world challenges. So it was interesting. So he kind of convinced me this was the killer app, but then I looked up his startup, which is called Bliss, just like this morning, and it turns out now he does enclaves for AI. So draw your own conclusions. So the future. So the future is bright for FHE. So I found that I was already putting together too many slides. So I'm going to focus on one of these. So first of all, hardware acceleration. I think it's going to get a big boost from AI hardware acceleration, because the issues are kind of similar, and I'll describe why in a minute. Another aspect that I think has to be dealt with is that I think we need better proofs for correct FHE evaluation. So first of all, just because I think it's kind of needed for FHE security, because if you have a fully malleable scheme and users are kind of convinced to act as decryption oracles when maybe ciphertexts are not valid, then that can be very dangerous. In some cases, you can recover secret keys. So it would be great if there were proofs of correct FHE evaluation, so that before you decrypt, you can verify this proof, be sure that it's a valid ciphertext, and then safely decrypt it. I think it would also be great for a secure AI model ecosystem. So basically, it would be cool in the future if we just had all sorts of different models and different data sets And you could prove that this model was, initially trained on this high quality data set, and then it was fine tuned on this data set, and it was trained in a way that, there are no trapdoors in the model, and the data set is such that there's no data poisoning attacks for the model. It'd be great if you could prove all of these different things about models and data sets, so that this is really the trust that you need to build an ecosystem of AI and of models and data sets. Without it, it's harder to build that ecosystem. And then finally, the main thing I'm going to talk about is I just wanted to talk about one technical result that was really interesting, since most of my talk is fluff. So in particular, I want to say sort of mea culpa, because a lot of my my early presentations had this claim that FHE is in the circuit model. It doesn't do RAM computation, so please don't expect it to. But it turns out now that it does do RAM computation. So I want to show how that works. So I'm going to breeze through, and I just want to make, before I get into the RAM computation, FHE for RAM, I just want to mention this one hardware acceleration point that I noticed. It just caught my eye. I was reading about some AI stuff, and there's this chip by a company called Groq, G-R-O-Q, and it's just a chip, and their whole idea is just that neural networks are deterministic. I mean, they're not, it's not some sort of dynamic computation, right? It's just a deterministic fixed network graph with, the weights could be anything, but the computational graph is deterministic. So you know that at compile time. And so instead of trying to do all this kind of dynamic routing, which happens, sometimes during other computations, they can just do away with that and use the determinism of the circuit to predict exactly how things should be routed so that they get where they need to be in just the right time. So that obviously applies equally to FHE computation, and in particular to bootstrapping, because it's a fixed circuit, deterministic, and you just if you don't have to worry about all this dynamic routing that would otherwise happen inside the chip, you can just do away with that and get 10 times better performance. So I see that as being a pattern in the future, hopefully, that really people are going to be heavily motivated by hardware acceleration for AI, maybe less so by hardware acceleration of FHE, but hardware acceleration for FHE will benefit from the efforts for accelerating AI. Okay, so I just want to talk about this one result. It's not my result, but I think it's kind of the most theoretically interesting results that I've seen in the past 2 years, just because I didn't think it was possible. And so the basic question or example, I guess, is private Google queries. Can we do them? So is it possible, is it feasible to use fully homomorphic encryption to do a Google query in a semi-practical way? Now, I mean, there are a lot of, who knows exactly what's involved in a Google query, right? But I mean, there's some aspect of computing on the query, but there's also all sorts of magic tricks that Google does to minimize processing time. In particular, it uses things like inverted indices and all these sublinear data structures that allow Google to sort of zero in on the, quickly on which web pages it should be sending back, instead of just sort of linearly scanning all of its data. So one unproven claim, I mentioned before, they should be suspicious of unproven claims that things are impossible. But the claim that I made is that Google queries are always inherently going to be impractical, because FHE is in the circuit model, and if you want to do a Google query, the entire internet has to be basically an input to that circuit. So that means for each query, Google has to process the entire internet. And that's not going to be at all efficient compared to what it does now, which is use all sorts of sublinear data structures, random access memory, to make the internet search happen in a fraction of a second. So as I mentioned, though, these guys proved that RAM FHE is possible. So this is Lin, Mook, and Wicks. And there's a Quanta article if you want to read about it. That's where these pictures came from. And so how does it work? So what does a RAM computation look like, first of all? So this is kind of an abstraction of what it looks like. Basically, you have a lot of different RAM steps. In each step, you have an input to that step, which might be some state. And it goes into the CPU, and it outputs the next state. And it also outputs an index that you can look at in memory. And what you want to do with that index is you'll have to take it and you'll have to go to that place in memory and retrieve that memory and input that into the next RAM step, right? So that's RAM computation. So if you think about applying FHE to this, well, it's pretty easy to apply FHE to each individual RAM step, right? So all the inputs are there. You just run the CPU computation using FHE, and you get output, some encrypted state and some encrypted index. The problem is, what do you do with that encrypted index? I mean, you don't know where to go. It's encrypted. So you have to somehow convert this encrypted index into the memory at that index. So you have to change I to M of I. But actually, that looks like a private information retrieval problem. So if you just view M, the memory, as a database, that's exactly what you're trying to do in private information retrieval. You're trying to take I and get back the ith bit of the database. Okay, so, but it seems like, I mean, for private information retrieval schemes that we knew about, well, they suffer from the same problem that the server has to process the entire database for each query. So that doesn't really seem to help. But what if we had something like a RAM version of private information retrieval? That might help us. Okay, so what is our strategy for doing that? I guess, is it even possible, first of all? So here's private information retrieval again. So basically, Alice has I. She wants to get TB of I without revealing I. So the unproven claim, the intuition, is that the server computation should be inherently order the size of the database. Why? Because if there was some portion of the database that the server didn't read, then the server itself would know that portion was irrelevant to the query. So the server can, kind of figure out, seems kind of silly, but if the server was somehow sublinear and didn't actually read everything, and yet it still managed to respond to queries, then that seems to imply that the server already knew that portion of the database was irrelevant, which of course it can't know. So that seems like pretty uncontrovertible evidence that the server computation should be inherently order n. But, there's kind of a way around this. Let's say the server doesn't just, keep the database as it is, but instead preprocesses it in a way to get DB prime. It does this one time for all clients, and maybe that preprocessing causes some expansion, but maybe that preprocessing sort of, interleaves the database bits in some magical way so that you can't any longer say that, if I just access a few bits in TB prime, maybe it doesn't follow that the server knows that some bits are irrelevant. Yeah, so anyway, so the idea is that Alice will access this preprocessed database DB prime, just a few locations, and somehow it will cover DBI. It will cover DBI without revealing I. So you want that, the query complexity and the response complexity are both really low. In particular, response complexity is like polylog n instead of n. Okay, so so how can we possibly do that though? So well, let's consider kind of a related problem. So think about, forget about databases for a minute, just think about polynomials. So let's suppose you have a polynomial. It's p, evaluated at x1 through xm, degree d, and it has, you can think of it as univariate if you want initially, but it's, in the scheme it's actually going to be multivariate, and it has n monomials, okay? And let's just say I want you to preprocess that polynomial in a way that you can evaluate it really fast for any input. Okay, simple question. How would you do it? Well, you get kind of the same impossibility result if there's no preprocessing of p allowed. In general, because you would have to read kind of the coefficients of p each time you evaluated p, right? If you weren't allowed to preprocess p in any way. So in that case, evaluation time is still order n. But if there's preprocessing, well, here's a really simple idea. You just compute and store all the evaluations of p at all the different inputs. Okay. So once you've done that, then obviously the random access time of evaluation is really easy because you just go to that location for corresponding to the input. Okay. So in particular, so how many different inputs are there though? Well, there are q to the m different inputs if we're evaluating this polynomial at mod q. So there are q to the m different possible inputs, and you would have to store the evaluation at all of them in order for this trick. Okay. Well, that could be bad. So what if q is huge? So if q is really big, say maybe q is exponential and n, who knows? What do you do if q is huge? Well, I mean, if q is smooth, we'll say q is just a product of a lot of small primes. All these small primes are smaller than d. So q to the m is basically smaller than d to the m, which is n. In that case, you could just use CRT. You just do this trick of evaluating p at all the inputs, modulo each of the different small primes, and you just keep a different, in your preprocessed database, you just store for each of the t primes, you just store all of those different inputs. And so, for example, mod q1, there are only q1 to the m different inputs possible. So you only have to store that, which is much smaller, right? Okay, so that's actually kind of efficient. Okay, well, that works for smooth q, but what if q is just really huge and not smooth? Well, it turns out there's this crazy theorem by Gödel and Umans for 2008, which basically gives you the best you could possibly hope for. And it says, let R be a ring of cardinality q. I mean, it could just be, integers mod q if you want to think of it that way, but it could be a more general polynomial ring of cardinality q. Okay. All right, and let p be a polynomial in that ring of degree d, individual degree d, with n, at most n monomials. Then it turns out that for any epsilon that you want to pick that's greater than 0, and as long as n is sufficiently large, you can preprocess that polynomial p into a data structure of at most size n, and here you have some fancy stuff, n to the 1 plus epsilon, and then log q to the 1 plus little o 1. Okay, so a data structure of that size. I'll just say, by the way, what is the initial size of p? Well, p has n coefficients, right? And each of them is mod q. So just storing p natively takes size n log q. And this is saying this new data structure is only going to be a little bit bigger than that. It's going to be n the 1 plus epsilon and log q to something a little bit bigger than 1 instead of n log q. So just a little bit bigger. And that data structure allows you to allows random access evaluation of that polynomial at any input in time, which is basically poly log n. I mean, of course, the log q is there because we're working modulo q, but basically poly log n time. So it's a pretty amazing result. It says that basically once you've done this pre-processing, the evaluation time really doesn't even depend on Q that much. I mean, you could have a really huge Q. It just really mostly depends on the number of monomials in that polynomial. But the Q, the size of the ring that you're evaluating over can be basically almost arbitrarily large. Okay, so how are you going to use this to get RAM private information retrieval? So, all right, so Netflix has this database here. What they're going to do is they're going to find a polynomial that evaluates to that database. Okay. So if you look on the left-hand side, so the index I that Alice looks for is going to be sort of decomposed into m different variables. You just kind of split it up into different bit segments, right? And then that will correspond to this polynomial here, the database polynomial p sub db. And it's going to be a polynomial just like we described. It has m variables in degree d, and with the property that at basically p db of I equals the database of at I. And that's going to, that equality will hold over what ring? It'll hold over the plain text ring that we're using for our homomorphic encryption scheme. Okay, so you just set p that way. Okay, to evaluate to the database. Okay, and since d to the m is bigger than n, basically there are enough degrees of freedom, enough monomials in PDB that you can set the coefficient so that it will evaluate to the database. Okay, and then what does the server do with that polynomial? Well, it pre-processes it in just the way that Gödel and Umans say to. However, we do that kind of with respect to a different ring. So initially, PDB was defined with respect to the plain text ring, but we're going to do all this pre-processing of PDB with respect to the ciphertext ring, the overlying ciphertext ring. Okay, and you'll kind of see why in just a second. And as I mentioned before, the size of the ring almost doesn't affect the complexity of this of Gödel-Umans result. You still get fast polynomial evaluation even when we're doing evaluation over a really large ring like the ciphertext ring. All right, so that's the DB prime. That's kind of the post-processing of the database. What's Alice going to do? She's just going to encrypt the segments of her index. And what would you expect in the FHE scheme to happen here? What you would expect, well, the server is just going to evaluate this database polynomial at the ciphertexts. What should it be? The final ciphertext should encrypt dbi, right? That's just the way the polynomial is defined. But the wrinkle, the reason this all works is because the trick is that this scheme uses is that rather than using one of the modern FHE schemes, Lin, Mook, and Wix use kind of the old-timey algebraic, somewhat homomorphic encryption schemes where literally evaluation of a polynomial over ciphertext was was f of those ciphertexts. Okay, so modern schemes have modulus switching and all sorts of fancy tricks to keep the noise small and so forth. But back in the old days, like the very first scheme, my scheme, so early Bukursky-Vaganathan scheme, before all these tricks, literally you would do something like you basically do the way you would evaluate a polynomial on ciphertext is literally to apply that polynomial to those ciphertexts. Okay, and if you use a scheme like that, then you can directly apply the Kedlaya-Ullmann's result, where you just go back up to this evaluation and say, hey, it's really just literally this polynomial applied to those ciphertexts. And since that's what it is, this whole Kedlaya-Ullmann's trick of preprocessing that polynomial works. You know, even though those ciphertexts are in a gigantic ring, there's a way to basically Alice will only access a few slots in this DB prime corresponding to what she needs to evaluate this polynomial at these inputs. And you know, the server won't be able to tell exactly what she's looking for because, well, I mean, Alice is only sending Netflix ciphertext, so of course they can't determine what exactly her query corresponds to in terms of plain text index. Okay, so this scheme is kind of inefficient. So of course, the old-timey algebraic, somewhat homomorphic encryption schemes themselves are inefficient. And the total degree here that's embedded in this polynomial PDB is basically dm, where d to the m power is n, the size of is bigger than n, the size of the database. So d and m can be like log big N. This is like log squared n. That's a pretty, I mean, you know, it's a pretty big degree. So that's the main reason why this scheme is inefficient right now. Maybe there's some way to replace this technique and use more modern FHE schemes to get better performance here. If so, that would be great, because right now this FHE, RAM FHE scheme is not terribly practical. For right now, we're just still discussing RAM private information retrieval. So I just want to give you the final step, wrapping it back up from RAM PIR to RAM FHE. So if you recall, we could do each of these individual RAM steps inside FHE. The problem was just going from I to MI, right? And so just to explain fully what happens, there's a step where you take the FHE cipher encryption of, say, F1, and you convert it to an encryption inside the algebraically somewhat homomorphic encryption scheme, decomposed into these m different segments. You know, I mean, you can do that because, well, I mean, this adds additional complexity because basically you have to perform FHE decryption inside the ASHE scheme. So that increases the degree even more than it was. But doable in principle. And then you do use the old time ASHE scheme to do an evaluation of that database, that memory polynomial. M stands for the RAM memory here, using Kedlaya-Ullmann's RAM-based approach. Okay, and then you convert that back to FHE in the usual way, and you just keep going like that. You're just alternating between the FHE schemes and the algebraic schemes. Okay, so aspects I didn't cover. So yeah, I kind of assumed here that the memory M is static. Of course, the RAM memory is not going to be static. So there are techniques that they describe to handle memory updates, and they're, you know, asymptotically reasonably efficient. And I didn't describe, you know, the fancy workings of Kedlaya-Ullmann's to how exactly they do this super fast polynomial evaluation in general. But it's not too complicated. So I kind of touched upon it with basically it's CRT. It's you know, if you know that your Q is not a smooth number, basically you have to do things over the integers. So like, treat the equation modulo that big Q as an equation, over the integers where, there's some reduction modulo Q step afterwards. So you go, and then you need to pick enough primes so that, even that mod Q reduction doesn't have an effect. So anyways, it's kind of a recursive application of CRT. So the principles are sort of similar. So the open questions are, so this is a very ring LWE based scheme because it's all about kind of polynomials, evaluating polynomials over the actual ring used in the ring LWE scheme. How do you base security on an LWE based scheme? So that's an open question. And how do you improve efficiency? So, I mean, there are many layers of inefficiency of the scheme so far, but, the same could be said of my 2009 scheme. So it's early days, and hopefully, if people look at it, this could be much faster, and we could have asymptotic and practical improvements on the order of what we had for the first FHE schemes. And also just this Kedlaya-Uman's trick is kind of interesting. Like, I mean, given that we now know that you can pre-process polynomials to evaluate them unusually fast, it seems like this could have other applications in crypto. So one thing that comes to mind is polynomial commitment schemes used in snarks. But still, we would have to get the efficiency because even Kedlaya-Uman's technique has its overheads. So it'd be nice to get those down. So that's all I have. Hopefully it wasn't too much. Thanks.